Assalamu alaikum everyone. Welcome to the course of ME212 Dynamics. This is lecture 30, and in today's lecture we will cover the topic relative motion analysis using rotating axis. Dear students, in the previous sections the relative motion analysis for velocity and acceleration were described using the translating coordinate system. So there may be a case when a rigid body is connected in such a way that the sliding will occur at their connections. So in that case, the most suitable technique is to use the axis that translate as well as rotate. So moreover, when the case is in such a way that the 2 points are not lie on the same rigid body, like in the previous case, the point A and point B that we consider for analysis lie on the same rigid body. There may be a case that the points are not lie on the same rigid body. So in that case, the most suitable axis that must be on the rigid body is the rotating plus translating axis. So such type of analysis is useful in that case. So in this lecture we will discuss this analysis and provide the velocity and acceleration analysis for the relative motion using the rotating axis. So let us say that you have a rigid body. Let us say that this is the rigid body, and this rigid body has 2 points. Let mark that point A and point B, and you have a fixed inertial frame of reference. Let us say that capital X and capital Y show the fixed inertial frame of reference. So imagine that you have you have axis on the rigid body. Let us say that small x and small y show the axis on the rigid body. So in the previous lecture we discussed that these axes which are on the rigid body are the translating axis. That when the rigid body move, it only translate, it does not rotate. But there may be a case that when the rigid body move in such a way that these axes instead of translation it also rotate. So let us say that the new location of the axis on the point B will be this one. So it make an angle of theta with the original position of the axis. So this was the original position x and y, and it make an angle of theta. Similarly, it move further in this way, and the axis new location become this and this one. So it make an angle of theta. It's called xy, and new location is xy, x prime and y prime. So it make an angle of theta with the original axis. So in this way the axis on the rigid body translate as well as rotate. So in this lecture we will derive the velocity, position and acceleration equation for the relative motion analysis using rotating axis. Now to derive the position equation for the relative motion analysis using rotating axis, imagine that you have a rigid body. Let us say that this is the rigid body and this is your fixed inertial frame of reference, capital X, and capital Y is your fixed inertial frame of reference. And you have 2 points or 2 particles on the rigid body. Let us say that particle A and particle B are the 2 particles on the rigid body. So imagine that at this instant the axis location on the rigid body is X and Y, which are at an angle or which are tilted. So how can we find out the position of the particle A with respect to the inertial frame of reference? We have to draw the position vector. So let us say that the position vector for the particle A is RA, which shows the position of the particle A with respect to the fixed inertial frame of reference. So inertial frame of reference is such that on the inertial frame of reference acceleration is 0, so it is fixed, and all the Newton's laws can be applicable to the inertial frame of reference. So what is the position of the particle B with respect to the inertial frame of reference? Again we have to draw the position vector. So let us say that the position vector for the particle B is RB. Now what is the position of the particle B with respect to the particle A? As the axis on the rigid body is on the particle A, so so in this case the particle A become our observer and particle B become object. So we have to draw the position vector from the observer to the object. So this is our position vector. So it shows the position of the particle B with respect to the particle A. So in this way by the vector algebra we can write that RB equal to RA plus RB with respect to A. So this is the position equation for the relative motion analysis in case when the axis rotate. So in this case, in this equation, RB with respect to A can be written in the form of X and Y, as the position of the particle B can be measured from the axis on the rigid body, which is the small x and small y axis. So what is the position of the particle B from the x-axis and from y-axis. Let us say that it shows the position of the particle B from the x-axis. So this will be your y location. So what is your x location? This is your x location. So we can write our B with respect to A is xi plus yj. So in this way we can write the above equation is RB equal to RA plus xi plus yj. So this is the equation, this is a position equation for the relative motion analysis using rotating axis. Now to find the velocity for the case of the relative motion analysis using rotating axis. So velocity can be found out by taking the time derivative of the position. So the position equation that we derive in the previous equation, in the previous slide, was RB equal to RA plus RB with respect to A. This was the general equation. So how can we find out the velocity from this equation? By taking the time derivative. So by taking the time derivative, d by dt of RB equal to d by dt of RA plus d by dt of RB with respect to A. So A is the position RB and the position RA is measured from the fixed inertial frame of reference. So we can call this as the absolute velocity. So we can write this as VB equal to VA. Now as RB with respect to A is measured with respect to the axis on rigid body which rotate. So in this case it can be it is not like possible to write it as VB with respect to A or simply VB or VA. So we have to think about this. So in the previous slide I also write RB with respect to A is xi plus yj. So by substituting the value of RB with respect to A, so we get the equation VB equal to VA plus d by dt of xi plus yj, where I and j are the unit vector of the axis on the rigid body. So again imagine that this is your rigid body, this one is your fixed inertial frame of reference, capital X and capital Y. Let us say that this is your particle A and this one is particle B. On the particle A you have axes which are the tilted axis, which are small x and small y. So imagine that I and j are the unit vectors on the small x and small y axis. So this is your I vector and this one is your j vector. And imagine that on the capital X you have I unit vector and here you have capital J unit vector. So in this case as this axis the unit vectors on the as the axis xi and yj, here the unit vector I and j has a magnitude 1 but it's changed its direction. So it means that we can't take I and j as a constant, so we have to take consider them in taking the derivative. So by taking again the derivative, VB equal to VA plus, here we have to take the product rule. So by taking the product rule it become dx by dt time I plus x time d by dt of I unit vector, similarly plus dy by dt time j plus y time d by dt of j unit vector. As the unit vector changes its direction, although it has magnitude 1 but it's changed its direction. So as the direction is changing, so it means that its direction is changing with respect to time, so it must be considered in taking the time derivative. And similarly the position of the particle B also change with respect to time. It means that the the x distance and the y distance also change with respect to time, so we have to take them, consider them in taking the derivative. So by considering the position vector and also the x and y position in the taking time derivative, the equation become VB equal to VA plus time derivative of the position x time unit vector plus x time derivative of the unit vector, similarly for the y. So we can write this equation as VB equal to VA. So we can combine the time derivative of the unit vector in separately, and the time derivative of the position separately. So it become dx by dt of I plus dy by dt of j plus x time di by dt plus y time dj by dt. So here in this case is dx by dt is your component of the velocity in the x direction, and dy by dt is the component of your relative velocity, as here I and j are the unit vector in the on the rigid body, for the axis on the rigid body, so it can be considered as the relative. So it shows the position of the particle b with respect to the particle a. So it means that dx by dt and dy by dt is the components of the relative velocity of the particle b with respect to particle a in x and y direction. So we can write this as vb equal to va plus, so we can write it as v of b with respect to v of a time x. It shows the position of the particle of the particle b with respect to the velocity of the particle b with respect to particle a, plus vb with respect to particle a in the y direction time j. So we can write this in this form, plus x time di by dt plus y time dj by dt. So in the previous slide, the last equation that we derived was vb equal to va plus it was vb with respect to va in the x-axis I plus vb with respect to a in the y direction time j plus x time di by dt plus y time dj by dt. Here I and j are the unit vector. So as this is the components of the velocity in the small x and small y direction, so we can call this as vb with respect to va is a whole velocity, as these are the components. So we can call this as vb with respect to va in the x, y or z. If we take the third component as z, so in the x, y, z. Here in this case, as the motion is in the x, as the axis translate only in xy, so we can call this as xy. You can simply write this xy, or you can if you don't want to write xy, so it does not matter. So the above equation become vb equal to va plus vb with respect to a plus x time di over dt plus y time dj over dt. So in this equation we have to find out the time derivative of the unit vector I and time derivative of the unit vector j. So how can we find out the time derivative of the unit vector? So imagine that at the current location, this is your I unit vector and this one is your j unit vector. So imagine that after some time these axes rotate. So the new location of these axes become, this one is your I prime and this one is your j prime. So this is at very small instant dt. So it make an angle of d theta here and here d theta. So what is this? This is basically your di change in unit vector, and what is this? This is your dj, which is change in unit vector. So what is the magnitude of the unit vector? The magnitude of unit vector is 1. So by using the s equal to r theta or radian definition, what is di? Di equal to 1 time d theta. So by dividing both side by dt, it become dt. But here on the right hand side, on the one side you have vector, on the other side d theta by dt is scalar. So you have to multiply by a vector. So what is the direction of di? So the direction of di is, as can be seen that here, this di is in the j direction. So we can write here is this is j. Similarly, what is dj? So dj equal to the magnitude of the unit vector j is 1, is j and I are the unit vector, so it become 1 d theta, again dividing by dt. On one side you have vector, on the other side you have scalar. So on multiplying the vector to have a same equation, dimension of the same equation on both sides. So what is the direction of dj? So as can be seen that dj is in the I direction, in the negative I direction. So we can write here is minus I. As one is in the as dj can be seen that here it is in the negative I direction. So here you can substitute the value of di by dt and dj by dt in the above equation. So the above equation become vb equal to va plus vb with respect to a plus x time, what is d theta by dt with respect to time. As d theta is a change in the angular position is for the axis, as d theta is the axis that rotate. The x-axis and the y-axis rotate through a small angular displacement d theta. So we can write the angular displacement, we can write the rate of change of angular displacement for the axis as omega. So this omega is here written, can be used for the axis angular velocity. So d theta by dt is the angular velocity, but this angular velocity is not for the rigid body, this angular velocity is of the axis. So for the axis, the nomenclature used here, the symbol used for the angular velocity is omega. You can see here, this is the omega. And for the angular acceleration, we can simply write as omega dot. This is for the axis on the rigid body. So it can be written as x time, what is d theta by dt, this is omega time j, okay, plus y time omega time minus y minus I. So by writing the above equation in the cross product, so in the cross product, as we know that, let us say that this is your I, this one is your j, and this one is your k. So as omega is out from the board, it is always in the z direction, so it means that omega vector is equal to omega time k unit vector. So when we how can we cross multiply k with any of the unit vector to come with j, as here we have j. So when we cross multiply k with I, so it gives us j. So it means that we can write this equation as omega cross I. We can write this omega j equal to omega cross I, because the cross product of omega with the unit vector I give us omega magnitude time j unit vector. So how can we multiply omega with any of the unit vectors so that it gives us minus omega I? So as omega is in the k unit vector, has a k unit vector, so when we multiply k with j, it gives us minus I. So it means that we can write this as omega cross multiply with j. So in the previous slide, the velocity equation that we derived was vb equal to va plus vb with respect to a plus x time omega cross I plus y time omega cross j, where omega is the angular velocity for the xy axis, which are the on the rigid body. So here we have x time omega cross I and y time omega cross j. So by using the distributive property of the cross product, that is by using distributive property of a cross product, So what is the distributive property of the cross product? It is that m a cross b equal to m time a cross b equal to a cross m b. If you have any constant which has to be multiplied with the cross product of the two vectors, so it can be the constant time for first vector time second vector, or first vector time cross product of constant time second vectors. This is your distributive property. So by using the distributive property, we can write x time omega cross I is omega cross xi. Similarly, y time omega cross j equal to omega cross yj. So when we write the above equation in this fashion, vb equal to va plus vb with respect to a plus omega cross xi, okay, plus omega cross yj. So in this we can take the omega as a common, so the above equation become vb equal to va plus vb with respect to a plus omega cross xi plus yj. So what is your xi plus yj? This is your rb with respect to a, as we derive this in the first slide of today's lecture. So the above equation become vb equal to va plus vb with respect to a plus omega cross rb with respect to a. So this is a velocity equation for the relative motion analysis using rotating axis. So in this way the velocity equation can be derived for the relative motion analysis using rotating axis. So in the previous slide, the velocity equation that we tried was vb equal to va plus vb with respect to a plus omega cross rb with respect to a. So this was the velocity equation for the relative motion also using rotating axis. So how can we find out the acceleration from this velocity equation? So by taking the time derivative, we can find out the acceleration. So by taking the time derivative, d by dt of vb equal to d by dt of va plus d by dt of vb with respect to a plus d by dt of omega cross rb with respect to a. As the position for the particle b and particle a was measured with respect to the fixed inertial frame of reference, so the velocity and acceleration for the particles with respect to the fixed inertial frame of the reference become our absolute velocity and absolute acceleration. So the time derivative of the position with respect to the inertial frame will become velocity, and the time derivative of the absolute velocity will become absolute acceleration. So it become a b, which is the absolute acceleration of the particle b with respect to the fixed inertial frame of reference, and this will be equal to a, which is the acceleration, absolute acceleration of the particle a, plus we can write this as a d by dt of vb with respect to a, as it measures with respect to the axis on the rigid body which rotate, plus here we can take the time derivative, we can apply the product rule, as omega is the angular velocity for the rotating axis, so it changes with respect to the time. Also the position of the particle b with respect to the particle a change with respect to the time. So both omega and rb with respect to a is a function of the time, so we can't take anyone as a constant. So by applying the product rule, we can take the time derivative of this quantity. So it's become d by dt of omega cross rb with respect to a plus omega cross d by dt of rb with respect to a. So this equation become in this way. So again, by writing this equation, ab equal to aa plus d by dt of vb with respect to a plus, here this term this is the time derivative of the angular velocity, so it's become angular acceleration. But this angular acceleration is for the axis, not for the rigid body. So we can write it as omega dot, which is the angular acceleration. This cross multiply with the RB with respect to A plus omega cross. What is your time derivative of RB with respect to A? So time derivative of RB with respect to A, as we derive this for the case of the velocity, and this was equal to VB with respect to A plus omega cross RB with respect to A. This was the time derivative of RB with respect to A, and this is derived earlier. So I can write here is derived earlier. So in the previous slide 6 or slide 5, you can see that how can we derive the d by dt of RB with respect to A. So the acceleration equation the part of the acceleration equation in derivation that we derive in the previous slide was AB equal to AA plus d by dt of VB with respect to A plus omega dot cross RB with respect to A plus omega cross VB with respect to A cross omega cross RB with respect to A. So this is the term that we derive in the in the derivation of the velocity. So as we know that A cross B plus C equal to A cross B plus, sorry, here we have plus sign. So as we know that A cross B plus C equal to A cross B plus A cross C. This is the property that we know. This is the property of the cross product. So by using this property, the above equation become AB equal to AA plus d by dt of VB with respect to A plus omega dot cross RB with respect to A plus omega cross VB with respect to A plus omega cross RB with respect to A. So this is the by using the property, the equation become this. So in this equation, all the derivative has been done except the derivative of VB with respect to A. So as we know that VB with respect to A is equal to VB with respect to A x component time I unit vector plus VB with respect to A y component time j unit vector. So consider the above equation as equation A. So by taking the time derivative, so d by dt of VB with respect to A equal to, here the component of the velocity as well as the unit vector changes with respect to the time. For the unit vector, magnitude will be the same one, but the direction of the unit vector change with respect to time. So we have to take both, we have to consider both in taking the time derivative. So this become d by dt of VB with respect to A in the x component time I unit vector plus VB with respect to A in term of x time di by dt. This is for the first term. Similarly, d by dt of VB with respect to A time y in term of j unit vector plus VB with respect to a y component time dj by dt, the j unit vector. This is the second term. So in the above equation, we can combine the unit vector derivative terms together. So the above equation become d by dt of VB with respect to A x I plus d by dt of VB with respect to A y in term of a j unit vector, this term and this term together plus this and this together. So this will be VB over VA x di by dt plus vb with respect to ay dj by dt. So the above equation become in this way, and this is the time derivative of vb with respect to a. So in this equation we have to find out time derivative of unit vector I and time derivative of the unit vector j. So as the time derivative of the unit vector we derived previously, and this was equal to omega cross I and omega cross j. So by substituting that values we can find out time derivative of vb with respect to a. So in the previous slide, the last equation that we derived was vb with respect to a equal to that was equal to d by dt of vb with respect to a into xi plus d by dt of vb with respect to a y in term of j. The first term of that equation plus second term was vb with respect to a x di by dt plus vb with respect to a y dj by dt, and the di by dt that we derive in the derivation of the velocity was equal to omega cross I, and similarly dj by dt was omega cross j. So by substituting the values, the above equation become d by dt of vb with respect to a equal to, now what is this equation? This is the time derivative of the x component of velocity, similarly time derivative of the y component of velocity. So this is the component of the this is the x component of acceleration and y component of acceleration. So we can simply write it as a of b with respect to a. We can simply write this in the x, y and z axis plus vb with respect to a x, and this is with omega cross I. Similarly vb with respect to a into y, and this is omega cross j. This is by substituting the value of di by dt and dj by dt. So the above equation become equal to a of b with respect to a plus, again using the distributive property, which is m time a cross b equal to a cross mb. So by using this property we can write the above equation as omega cross vb with respect to a x into I, similarly omega cross vb with respect to a y time j. So this is the time derivative of the velocity. So by substituting these values in the equation a of the in the previous slide, so we can get ab equal to aa plus a of b with respect to a plus omega cross vb with respect to a xi plus omega cross vb with respect to a y j. This was the value of the time derivative of vb with respect to a plus omega dot cross rb with respect to a plus omega cross vb with respect to a plus omega cross rb with respect to a. So in this equation, as can be seen here, that here this is omega cross vb a x and this is omega cross vb a y. So in this we can take the common we can take omega as common, so this become equal to, so I can write this in the next slide. So by taking the omega as common, so we can write this equation as ab equal to aa plus a of b with respect to a plus omega cross vb with respect to a plus omega dot cross RB with respect to A plus omega cross VB with respect to A plus omega cross RB with respect to A. So this is the equation that we derive. So in this equation, as can be seen here, we have omega cross RB with respect to A, and here omega cross RB with respect to A. So we can simply add this, so it becomes 2 omega cross RB VB with respect to A. So by simplifying the above equation, so AB equal to AA plus A of B with respect to A plus omega dot cross RB with respect to A plus omega cross RB with respect to A plus 2 times omega cross VB with respect to A. So this is the acceleration equation for the relative motion analysis using rotating axis. So in this way you can derive the velocity, acceleration, and the position for the relative motion analysis using rotating axis. So this is all about today lecture. So in today lecture we cover the last topic of this chapter, chapter 16, which was about the rigid body planar motion. So the last topic was about relative motion analysis using rotating axis. So today or tomorrow I will upload the lecture on by solving the numerical problem based on this topic. So in this way we have completed the chapter 16, and from next week we will start chapter 17. Thank you.